Hi everyone, my name is Nazlisha. In this video, me and my friends are going to talk about the volumetry analysis on industrial application and also the experiment on it. So, what is the volumetry analysis? Volumetry analysis is a method of quantitative chemical analysis in which the amount of a substance is determined by measuring the volume that it occupies, or in broader usage, the volume of a second substance that combines with the first in unknown proportions, more correctly called titrometric analysis, which is titration. There are three types of a volumetry analysis, which is the first one is direct titration, second back titration, and the last one is acid-base titration. Next, we're going to the industrial application of volumetry analysis. So, there are actually three types of industry that we can apply with volumetry analysis. The first one is textile industry. Volumetry industry is used in textile industry to know the actual concentration of bleaching agents used. Next, volumetry analysis is used in food industry to discover the amount of salt or sugar in a product or the concentration of vitamin C and E, which has an effect on product color. And the last one is environmental monitoring. It is used to measure the alkalinity and acidity of water samples to determine the presence of pollutants like acid rains, industrial discharge, and so on.
Next is direct titration. What is direct titration? It can be defined as a direct addition of standard titrant to the analyte in the presence of acid base until the reaction is complete and reaching the endpoint. The endpoint of the titration is typically indicated by a color change or by reaching a specific measurement on an instrument. These are some of the uses of direct titration. First is to determine concentration. It is used to determine the concentration of an unknown solution by reacting it with a titrant of known concentration. Number 2 is water analysis. It is used to measure the hardness, alkalinity, and chloride content in water sample. And number 3 is environmental monitoring. Direct titration is used to analyze pollutant and contamination in environmental sample such as soil and water. Let's go through to the calculation. A 0.2638 gram soda ash is analyzed by titrating the sodium carbonate with a standard 0.1288 mHCl solution requiring 38.27 ml. The reaction is Na2CO3 plus 2HCl produce CO2 plus H2O plus 2 NaCl. Calculate the percent of sodium carbonate weight over weight in the sample. For the volume HCl, we need to change it from 38.27 ml to 0.03827 liter. The concentration HCl given is 0.1288 m. So first we need to find mole of HCl, which is concentration times volume. So we key in the value and we get 0.00499 mole. Second is we need to find mole Na2CO3. 1 mole of Na2CO3 react with 2 mole of HCl. So we need to divide by 2. Mole Na2CO3 equal to mole of HCl divided by 2. Then we got the last answer is 0.002465 mole. Third, we need to find molar mass Na2CO3 equal to 2Ne plus C plus 3O. So we place the value, which is 2 times 23 plus 12 plus 3 times 16. Then we got 106 gram per mole. The next step, we need to find mass Na2CO3, which is moles times molar mass. So we key in the value, which is 0.002465 mole times 106 gram per mole. So we got 0.2613 gram. And the last step is we need to find percent Na2CO3, which is mass of Na2CO3 divided by mass of sample. So we key in the value and get 99.05% for the last answer.
Next is we're gonna talk about back titration. The definition is that a titration method used to determine the concentration of an unknown using an excess amount of a compound with a known concentration. The reason that we react to it with an excess of acid is to make sure that all of this base get used up, and then what we do is then we find out how much of our acid is left over by titrating our leftover acid with another base. The use of back titration is that we use back titration when the direct method of titration is not possible or it will yield an inaccurate result. The second is that in the case where volatile substances or substances that can evaporate very easily, such as ammonia, are being used, it will be impossible to yield a accurate result using normal titration, as some product will be lost during the titration. A slow reaction means the equivalent point, that is when the right amount of acid or base are reacting together to reach complete neutralization. It will occur before the endpoint. Other than that, the equivalent point of titration between weak acid and weak base may be very difficult to analyze due to the lack of suitable indicator. The example question as shown at the side. So first, we write a balanced equation for the above reaction. 2HNO3 plus CaCO3 will produce CaNO3 2 plus CO2 and H2O. And then the second equation, HNO3 plus NaOH will produce NaNO3 plus H2O. From the equation above, we know that 2 mole of HNO3 require 1 mole of CaCO3 and 1 mole of HNO3 require 1 mole of NaOH. In initial mole of acid total, we can calculate it by molarity times by volume, and we got 0.031575 mole. For the remaining excess during back titration mole, we can calculate by also molarity times by volume, and we got 0.007965 mole acid. For the mole of acid reacted with CaCO3, we can calculate it by initial of the mole minus with the excess of the mole, and we got 0.02361 mole. Next, we can also calculate the mole of CaCO3 in sample by timing the mole of acid with 1/2, and we got 0.011805 mole. For the mass of CaCO3 in sample, we got 1.1805 gram with all the mole that we have calculated before. And then for the percent WW of CaCO3 in sample, we will then divide the weight of CaCO3 by the weight of sample, then multiply by 100%, and we get 87.99% WW.
The next is about acid-base titration curve. An acid-base titration curve is a graphical representation of the pH of a solution during the course of an acid-base titration. Typically, it plots the pH of the solution being analyzed on the vertical axis against the volume of titrate, the solution of no concentration added to the analyte on the horizontal axis. So here the key feature of an acid-base titration curve include, firstly, initial pH. The pH of the analyte solution before any titrate is added, which depend on the initial concentration of the acid or base being titrated. The second is equivalence points. The point during the titration where stoichiometrically equivalent amount of acid and base have reacted. At this point, the pH is usually near 7 for a strong acid, strong base titration, but can vary depending on the nature of the titrates. The third is titration endpoint. The point where the indicator change color if an indicator is used, or where a pH meter shows a sudden change in pH. This may or may not coincide with the equivalent point. For the fourth is buffer regions. Regions on the curve where the pH change gradually with added titrate. These occur near the equivalent point and are influenced by the presence of conjugate acid pairs in the solution. 5 is shape. The curve can be steep or gradual depending on the strength of the acid and base being titrated and whether the titration is strong acid, strong base, strong acid and weak base, strong base and weak acid, or weak acid, weak base. The last is indicators. These are substances used to visually indicate the endpoint of the titration. They change color in response to change in pH and are chosen based on the expected pH range at the equivalence point. Understanding the titration curve helps in determining the unknown concentration of a solution or identifying the pKa of a weak acid or base. Next, this is example of question for acid-base titration curve. A HCl solution is standardized by titrating with a solution containing 0.2329 gram of primary standard Na2CO3 and boiled to remove carbon dioxide. The endpoint is reached when 42.87 ml of the acid has been delivered. Calculate the molarity of acid and sketch a titration curve for above titration. Indicate pH at the equivalent point. For the question, chemical equation balance is Na2CO3 plus 2HCl produced 2 NaCl plus H2O plus CO2. Firstly, find mole of Na2CO3. So 0.2329 gram divided with 106 G per mole, which is molar mass for Na2CO3. So we got 2.20 times with 10 power of -3 mole. Next, find a mole of HCl. 1 mole of Na2CO3 equal to 2 mole of HCl. So 2 times 2.20 times 10 power of -3, we got 4.40 times 10 power of -3 mole. Next is the question 1 to calculate the molarity of acid. So molarity of HCl is equal 4.40 times 10 power of -3 divided with volume in liter 0.042 at 7 liter. We got 0.103 molarity of HCl. Next is sketch a titration curve for above titration. For this is a titration curve for weak base and strong acid. For weak base is Na2CO3, strong acid HCl. So if first you have to sketch the curve. First you have to take a equivalent point. For this is equivalent point is pH less 7. Next is volume for HCl is 42.7 at 7 ml.
Next is experiment based on our topic, which is acid-base titration experiment. The objective for this experiment is to determine the percent weight over weight of the active ingredient acetyl salicylic acid C9H8O4 in aspirin tablet. Next, we will look at the procedure. There will be 4 methods, which is preparation of solution, where we need to prepare the 1 m NaOH solution, 0.1 m HCl solution, and 0.05 m Na2CO3 solution.
As for hydrolysis of aspirin, we use 25 ml of 1.0 m NaOH solution and 25 ml of water, then heat it for about 10 minutes in order to hydrolyze the aspirin. Next is standardization of HCl solution, where we use the procedure from past experiment to standardize the HCl solution. And the last one is back titration. The aspirin solution in 250 ml conical flask will be titrated for dilute 0.1 m HCl solution from burette slowly while shaking the flask. The procedure will repeat for 2 times. This is the result for the experiment. For table 5.2, standardization of HCl solution, the average volume of HCl is 26.3 ml, volume for Na2CO3 use is 25 ml, and the molarity of Na2CO3 use is 0.05 m. As for table 5.3, titration of aspirin solution with HCl, the average volume of HCl that we got is 10.57 ml, and the initial volume of NaOH used to hydrolyze the aspirin is 25 ml. Next, we will going through the calculation to find the percent weight over weight of the active ingredient in aspirin tablet. We use the back titration method. First of all, we need to find the mole of NaOH react using the formula moles initial of NaOH minus mole of excess NaOH. As for mole initial of NaOH, we use the formula volume times molarity, and we got 0.025 mole. Next, mole of excess NaOH, we need to find moles of HCl first, and after the calculate, we got 0.0132 mole for unreact NaOH. After that, we can calculate the mole of NaOH react, which is 0.0118 mole. To calculate the mole of ASA, we times 0.0118 with 1/2 because 1 mole of ASA equal to 2 mole of NaOH, then the answer is 5.9 times 10 to the power of -3 mole. After that, we can calculate the mass of ASA with the mole of that we got using formula mole times molar mass of ASA. The answer is 1.0629 gram. Finally, we calculate the percent weight over weight, and the answer is 103.76%.
By the end of this video, we can conclude that volumetric analysis is important to the industry such as textile industry, food industry, and also important as an environmental monitoring. By using all of the volumetric analysis experiment, which is direct titration, back titration, and the acid-base titration, we can say that the amount of wide range substances and its percentage can be determined.